Welcome, everybody, to another edition of Shape Shorts. I'm Stu Barr, and as usual, you'll see an empty chair here because Tony can't tell time. He studies time in physics, but he doesn't know how to tell it. Anyway, he's not here today, or he will be, but what we're going to do is interrogate him. God, I hate using that word. I meant interview Tony today. He's had a lot of discussion about physics and the state of physics in these days, and where it's going and what it's doing, and I wanted him to be interviewed. Now, he's going to say some really bizarre stuff out there. I want you all just to go, That's probably the best statement you can do. Now, as a little secret to all of you, I hate to say it, I may agree with him. But above all, do not let him know. Under no circumstances let Tony Patuco know somebody agrees with him. He gets a fat head. Wait. There he is. Hey, Tony, come on in. Where the hell have you been?
What are you guys doing here? You're here.
Sit down.
Oh, wait a minute. You set up already?
Sit down. Sit down.
This does not feel good.
Tony.
I think I've been set up. You said to be here at this time.
No, as usual, you were late.
Well, you're a half hour early.
You can't tell time.
That means there's something not quite right about
now,
this.
Here's what.
What's
can you
going
be
on?
quiet for 5
Okay,
minutes?
I can try. Okay.
Yeah.
Wait, did you work this with the director? You must
What
have,
did
because
I
you could
ask
not
you to
set
do?
this
What
stuff
did
up.
I ask you to do a minute ago?
You said just to come in.
I said be quiet.
Okay.
You already
I'll
forgot
listen.
that.
I'll
didn't you?
listen.
Okay.
Go
Now
ahead.
today, you and I have talked about physics, and I've titled this "Mathematics," the language physics used to write science fiction.
Well,
Now,
you
here's
finally
what
got it. You
Yeah.
finally got it.
Now, here's what I
can't
want you to do for the audience. You know this.
believe it. Did you introduce everybody already?
Oh, you're already on.
Oh my!
You missed it.
We're
Too
on.
bad.
We're on now.
Yeah.
Come on, you serious?
Yeah, I wouldn't lie to you.
Now,
Well, not this time.
Good thing you didn't. Anyway, continue.
So I want you to, before we get started, as kind of a level, explain to the audience how mathematics and physics function in a classical structure.
That's a very deep question, and I'm glad you brought that up because physics and mathematics have been so intertwined. And we've actually spoken about this through our classes many times, particularly in philosophy of science, how impactful mathematics was from the early days. And now we're going right back to, of course, Egyptian mathematics and Greek mathematics, how much it was related to the real world as they understood it. Pythagorean Theorem, the idea of the triangle, notion of point, line, and so on. And it became a description of the universe, basically. Their universe, our universe as we see it. And that culminates right through Galileo and right into the Enlightenment, which is really the engine for today's modern science. And then a very interesting thing didn't happen. I think why we brought up the science fiction part is because mathematics became more than a descriptor. We said in many episodes before this that how many times does it take one to look at a ball dropping from a certain height? It's hard to really get a sense of acceleration. You get a sense of velocity distance divided by time, but that becomes convoluted when you don't see acceleration, you see velocity. Galileo was able to make it more visible that there is a distinction between objects that are speeding up in time and objects that are not speeding up in time.
Could you do something here? Maybe I just heard some. Maybe for the audience, the Greek world I know, did they use mathematics or geometry? And maybe explains the difference.
Mostly geometry, and I'll rely on your expertise on this one. But I always had the firm belief that the Greeks were, I want to say it, I hope I don't offend anyone, but they were terrible mathematicians. They were excellent geometers, though. When you look at what Aristarchus and you look at Aristophanes, all these individuals, without geometry, they couldn't come up with certain ideas. Certainly, they didn't have an idea of rational numbers, or of irrational numbers. They had a good idea of rational numbers. They went from counting as 1, 2, 3, 4 items to the notion of count. Then it gets abstracted away to the notion of number. But they didn't take that step.
Did they ever? They never went to the concept of a number itself as an abstraction, correct?
No.
It was just empirically related?
Empirically related. For instance, take blocks, wooden blocks that children use. I hope they do still have wooden blocks.
No, they don't.
Because they probably plastic.
No, they count their cell phones.
Yeah, well, at least it's a block. All right?
Sort of, yeah.
Sort of. And 9 blocks, right? And it makes a nice square, 3 by 3. Realizing that you can make these geometries of these blocks very symmetric. And then if you take 4 blocks on each side, that's 16, right? You take 3 blocks on one side, that's 9 of them. And suddenly you put them together, another set of blocks is 5, that makes 25 blocks. So there's 25 blocks on, which is the longest side, the hypotenuse, hypo meaning larger side, and 16 here and 9 here, 9 and 16 is 25, and inside is a right triangle. The square on one side of a triangle plus the square on the other side of the triangle is the square that resides on the hypotenuse. If I take a leg of a triangle that's perpendicular, like this, take another one that's horizontal, make them perpendicular, 1 inch there, 1 inch there, and I, in essence, draw this hypotenuse, connect the 2 endpoints together with a straight line. And I take a drawing compass, remember the old days drawing compass, and I take that compass and I put the point here and the point here, and I rotate it down on a straight line. There is the square root of 2. It's somewhere on that line. I can't say it's 2/3 beyond 1.
Well, that brings up my point. If I have the two of them, then that tells me at this point the number has become an abstraction, not an empirical reality.
Absolutely. And number, once it went into the world of abstraction, which is, it's a big issue, because you ask, when did that happen? Well, right after Newton, it has to begin.
Yeah.
And in fact, right after Euclid, I think it has to begin, because Euclid had the same problem.
Well, maybe the Greeks couldn't understand a number as an abstraction rather than an empirical countable.
They knew it because of Pythagoras. They knew Pythagoras. They knew that he had gotten something, and I believe, and you'll know this, in the Pythagorean society, which became a society, which is always an issue when you have any kind of intellectual endeavor,
religion,
when you hide it behind a curtain. The society was, the secret code was the Pythagorean Theorem. A squared plus b squared equals c squared. Once they realize that there's a possibility that that hypotenuse is irrational, you lose the idea of measure. Now I can, as I said, I could take that, rotate it around, and find it on a straight line over here. There is square root of 2.
Whatever, yeah.
That. But the point is, I can measure it, but then again, I got a problem. Euclid never defined point other than saying it was something that has nothing. No width, no breadth, no length. And
The point is that which occupies no space.
no space. But a line is consistent of an infinite number of these points.
So how is an infinite number of no space?
I like
space.
and I know you would like that in your checkbook. I know if you went to the bank and you said, "Oh, I've got 0, but I got an infinite number of zeros, but they add up to 5 million, so I want it on my account."
I could pay
That's
Tony
what
the
a
money
straight
I
line
owe
is.
him now.
So when you ask about measuring a straight line, exactly.
He owes your money,
Yeah,
Tony.
exactly. So you see the contradiction.
0 times infinity is a million,
It's
Tony.
$1 million,
Don't worry
or
about
any
it.
number that you want.
Yeah.
Right.
So-
And that leads us directly into the idea of what Newton did with how to come up with a differential. He called them fluxions, and how you came up with the foundations of calculus, which became the idea that Leibniz would use at almost the same time.
Yeah.
So we should really have a discussion on Leibniz.
I think
as
it'd be
well.
great. And on the abstraction
And the
of
abstraction
mathematical
of
numbers.
mathematics. True that mathematics did kind of predict a kind of symmetry. The idea of a parabola, and those of the audience might remember that and hated it from algebra, has a shape. When you graph it, the graphing wouldn't come about until Descartes. Although, interestingly enough, I remember getting stuck in physics when I was in high school. One thing bothered me.
Only there?
Only there. Well, and
You were
I got
stuck when you were
I got
teaching.
stuck.
Come
I got
on.
stuck in day 1 in college. So I believe I've been stuck since then. And but I remember vividly there was a statement made in my physics textbook in high school where they kept using the word clearly. Like and it was something like average velocity and the average of two numbers are different. Average velocity is change in position over time. Average of two numbers is adding two numbers together, dividing by 2. Nothing to do with each other. And in this text, they simply equated them, which they had to do for the severely uninterested. And to me, I said, you're using equivocation, you're using the same word to mean two different things. A change in x over a change in time equivalent to the two numbers divided by 2, and one number being initial velocity, the second number being the final velocity. I didn't buy it. How I resolved my problem with this physics textbook at the time was going directly to Galileo's work. I just happened to have a translation of it to New Sciences, and in there he raised the same question, but he used a primitive graph, and that graph is before Descartes. I mean, they're almost the same, contemporary, not quite. Descartes will use a graph to generate this, but Galileo had used it several years before. And that's description. And then suddenly Newton comes along. The year that Galileo dies, Newton is born. Not much longer after that, 23 or 24 years later, and then suddenly mathematics became a predictor. And that's a long process, and that would extend itself to Newton. So using the idea of gravitation, which is, again, an extension, it takes another hour to talk about that, but gravitation is interesting in the sense that objects in the universe attract each other. And they attract each other universally around the universe. And if the universe is infinite, as they thought, then how does the mass know when other masses change? It has to be instantaneous. And this means that the universe is predictable. Get all the masses out there, and we've discussed this in philosophy.
The
of science
determinism.
Determinism. Yeah. You move one mass, the other masses know how to move. How does that happen? And then you have the notion of a predictor. And that is the point, I believe, where mathematics change, or physics change from using mathematics as a descriptor to using mathematics as a predictor. And you know the battle between Leibniz and Newton would come about by their definition of space. And suddenly mathematics took hold, and if it wasn't in the mathematical framework, then it had a problem with existence.
Would it be, let's move that up to the 20th century, would that be an illustration, for example, of the conflict between Mach and Boltzmann?
Oh, precisely, because Mach would hold to the Leibnizian view of space, which we should devote. And since you did this to me today, you're in for it.
What?
Your discussion about, we're going to...
You know, I can't hear you.
We're going to
I
discuss,
can't hear you.
We're
It's
going
going
to
bad.
discuss
Going
space
bad.
fairly soon about this.
Director, cut him out. Cut him out. Please cut him out.
Don't get him involved. He had like, I think he had 3 Bloody Marys today. I'm not really sure. Did you see the flask in his pocket?
Well, you know, he's still, maybe we should give him some more, because the more he drinks, the better job he does.
Well, let's hope. Let's hope. We're not sure how this is going to turn out. Anyway, but I think one of the clearest indications, other than space and time, which is a whole devoted series on that, is Paul Dirac. When Dirac made his rather famous equation, he saw that in the universe there should exist antimatter. Antimatter wasn't thought of. Antimatter would even be laughed at science fiction-wise, which is the title of the our talk here. Antimatter would not have been even discussed. And then suddenly, because the mathematics says it should exist, we look for it. And in a very short period of time, we find it. The positron is discovered, and suddenly mathematics becomes a really severe predictor. And then all of a sudden we start realizing if there's matter, there's antimatter. So on. All these things have to do with symmetry. And one of the greatest theorems ever written and proved was by Emily Noether in turn of the last century, who would not be allowed to teach at a university. Disgrace that this was the case. Why would you cut out 50% of humanity by saying you're a certain gender? It never made sense to me.
Because they're not as rational as they think they are.
Yeah, exactly. And her theorem is on the idea that for every symmetry in the mathematical world, there is a conservative force. Now, we have to recognize that that's an unusual
What does a
phrase.
conservative
What is a
force
conservative
mean?
force? If you throw a ball in the air, it rises with a velocity, reaches zero, comes back down, and reaches the same velocity at the end. It's a symmetry. Okay. And there are many...
That's called a conservative.
That's called a conservative operation. And we look for those in physics because conservative laws are very rare. They're not that obvious. What she said was the symmetry invokes this kind of conservation idea. That's incredible. And that theorem is remarkable. It's highly mathematical. It goes into the idea of certain kinds of symmetries, rotational and so on. And it's probably the most fundamental theorem we've ever had in physics. And that became kind of a touchstone. If all of that is based on a kind of an idea that there's a beauty in physics because of the mathematics. The mathematics has this beauty, therefore physics should hold to that. And we find all the time that this may be in question. Not right now, recently, several authors have come out and said, maybe our mistake is to associate that everything in physics should be within symmetry.
If we pull this up to the modern world, you have made this statement over and over and over and over and over again. Anyway, you've made the statement that physics seems to be frozen and stuck.
It does.
What do you mean?
Yes. I mean by that just what I said earlier, if we're bound by the notion of symmetries and beauty, then possibly the idea of anything fitting in that pattern that doesn't appear that way may be wrong. And when I say frozen is because if you can't, in essence, explain it, a lot of times physics invents it. And then, what's our director?
Well, he's got a good point.
What did he say?
Is symmetry leading to cul-de-sacs?
Oh, yeah, well, that excellent question. Did he actually do that? Did he write that?
You had him as a student.
Well, please, that explains a lot, though. That explains
and
anyway.
you got that right. Explains the drinking.
That's actually an excellent question, and I think it does. I think that I was attracted to physics day one because I was leaning towards the theoretical side. Having been an experimentalist for a little while, I moved into theory, and it was so attractive to be able to sit down at a desk with a pencil and write all this stuff down and realize I'm doing original math, and suddenly out comes something that could exist out there but isn't existent yet, and then it's found. That is a powerful way.
Well, let me ask you a question about methodology then.
Yeah.
Is instead of using almost a verification, an empirical verification principle, are we now using a mathematical verification principle in
Mostly.
science?
I think
or
it is.
not science, I mean
physics.
which would separate it from a lot of the other sciences.
I believe so.
Do you think how do you think that's going to affect the long-term of physics, its long-term future?
Here's an example. In biotechnology, we have seen more advances in biotechnology in the past, I'm going to say as recent as 7 years. We're in the middle of a pandemic, and how is it that suddenly we have a vaccine within 10 months? It's because it's been worked on for a very long period of time. The advances in that area are amazing. They combine computer technology, they combine molecular biology, structural biology. All these amazing areas come together. We haven't had a lot in physics. We've had inflation, we've had dark matter, dark energy, mostly by observation, twiddling with the idea of Einstein's field equation, which is maybe another lecture one of these days. Biotechnology really is a growing area like this. Physics used to be. I mean, every time you turned around in the 1970s, there was another particle, there was another this, there was another that. And a lot of the mathematics came out of group theory, and which is another area of mathematics that has to do with symmetry, was based on that. So it becomes almost excusable, since a lot of symmetry did produce a lot. You begin to realize maybe there's something here, and then suddenly it didn't. And then
When would you say that started? About
I'd say
10,
that
15 years?
in the 80s, 90s.
It wasn't. In other words, the mathematics as a predictor isn't working anymore.
I don't think so. I think it's, as a predictor, we want it to work, but there are so many. I don't know. I think Ivajolari's comment about cul-de-sac. We go from cul-de-sac to cul-de-sac, and I think you've been in subdivisions like that. You're in the right subdivision, but you're not at the right house. You know, and everyone gives you a turnaround. And every time we try to apply new mathematics to something, we find ourselves in kind of the same cul-de-sac, maybe a different street. Okay, and then we have a major problem. And roughly at the beginnings of quantum mechanics, we have what's called the Copenhagen interpretation, the Heisenberg interpretation, where now we have multiple universes. We have a multiverse idea, where, and I think you have a good shirt on today, is that right?
Yes,
Wanted, dead and alive, Schrodinger's cat, which means you automatically have a problem when you look at the notion of the collapse of the wave function, that you're in a multiple state of existence until you look at it. But the problem with that is, and I remember this as a graduate student, who looks at it? Do I look at it and suddenly the wave function collapses and the cat is alive, or the cat is not alive? And as a result, we may have a problem with the idea of quantum entanglement, and it's real because experiments are showing that if I polarize a photon this way in this part of space, a coupled particle or photon will also generate a change in polarization instantaneously, which violates the notion of
it's instantaneous across the universe.
Which is violating of the notion of the constant speed of light, which is a Maxwellian idea that was picked up, of course, by Einstein. And speed of light may not be constant. It may not be finite at this point. So how do you get away with that? And there are certain theorems that suggest this is fixable and it's okay. But you look at it very carefully, it does come from the idea that two areas, gravitation and quantum mechanics, the very large and the very small, we begin to lose that sense.
We got it.
Well, you see, it's that flask. It's got that flask in his back pocket, right? And
we got to keep an eye on it.
We got to keep an eye on it.
Well, I want to ask you a question now. We're getting near time.
Yeah.
As you see, what do you think can sit there and fix or move physics forward? What do you envision as moving that forward? As a solution, you brought up some stuff, but what's the solution to it?
I think one of the things in the inspirational six we came up with was dos ex machina, where we are put into a situation right now where you're either this or you're that. If I come in and I say, well, I'm questioning the foundations of Einstein's gravity, well, I might be considered a heretic. If I come in and I say, well, maybe you ought to go back and look at space and time again in a certain way.
Well, give definitions. Do we even know what they are?
Exactly. We can measure them, but what are we measuring is the main issue. And that's be a good topic for the next one. I might grill you on that one from the philosophical point of view.
Yeah, because it's a problem.
It's a
I can tell you what time it is. I can't tell you what time is.
Exactly.
And that's a big issue. Space is the same way.
And
what's space?
One of the misconceptions about Einstein is that he redefined time. No, he didn't. He redefined how we measure time and the concept of simultaneity and how we have to worry about the speed of light being fixed and constant. He didn't determine what time was. And it says that. I'm not going to tell you, like the Augustinian approach. I know what time is, but ask me to define it, I know not.
Yeah.
And that has gone through history for all this time. But when we are stuck in a world where we have the quantum mechanics of a wave function based upon the idea of probabilities of existence and non-existence at the same time, until we observe it. But the problem is, what's observation mean? If I hold a flower up and have the flower look at it, is that an observation? Does the wave function collapse then and determines whether the cat's alive or not? And
What if the cat observes himself in a mirror?
Exactly. What happens? Exactly. So you can go all of these paradoxes. So there are many, many more paradoxes. Several paradoxes are solvable. Zeno's paradox, we know that's all solvable. The idea of the twin paradox and relativity, solvable. These are not major paradoxes. There are fundamental major paradoxes that are still under inquiry. And the fact that I think physics has become so compartmentalized into the idea that the mathematics is going to tell us everything may be wrong. At least may be subject to re-examination. Well,
now you've heard from Tony. I feel very good about hearing that.
You know,
anyway,
you didn't fall asleep. Normally, when you usually go out.
No. Now, everybody, I want you to know he came in late. That was a blessing for all of us.
No, I didn't come in late. I came in on time. You deceived
me. You don't
me.
know what time is, so how would you know if you came in here? You
because
can't even
I have
tell
a
it.
concept of the old-fashioned notion of time and entropy.
You don't even know what old-fashioned is.
Arrow of time tells me that I'm
What do you mean an arrow of time? Where did you get that word from?
Obeying anthropic principles.
Oh, an anthropic one. Throw another word out there.
I am in the middle of a great disorder.
You know what he said?
You
Remember he
and
said
the
I
director.
didn't. You know he said I didn't fall asleep, but it was.
That's mostly your position.
So, but I want to thank everyone for being here with us, and we'll see you again on another issue of Shape Short.
Thank you, Stu. Good to see you today. Thank you.
Thank you.